let us consider one more theorem in that line, what we discussed in that problems, how to circumvent those problems that I discussed in last video. Suppose that our linear equation x dot t is equal to a t x t is uniformly exponentially stable, and there exists a finite constant alpha such that non at is less than is equal to alpha for all t. Then we can write qt is equal to this, the quadratic means the symmetric matrix that we are going to construct in this way can be written in this manner, and this is going to satisfy all the requirement of our original equation of that 9 and 10, and together with the hypothesis of that theorem, it is going to satisfy that. Let this be equation number equation number 1. So this is going to satisfy that. And one thing that is very striking here is that see here, if you want to deal with this problem, then what is the advantage this one is giving you? Instead of checking or finding out such a q without having any information a priori, here you are having one AT. Anyway, you must know AT, otherwise you cannot proceed with any calculation. And then just checking the norm of AT, it is sufficient for us to go for that. Like once you calculate AT, find that it is bounded by this A alpha, then you are able to construct qt, and then you will find that qt defined in this way. This is the definition you are doing for qt, is going to be your means satisfy all the requirements of our theorem of exponential stable system. And here one thing, this phi t, obviously they are representing the transition matrix. But then obviously one question may come that again that implies we need to calculate the transition matrix. What we are looking for, that transition matrix could be avoided, calculation of transition matrix could be avoided. Now here the catch is that so apparently it may gives you an impression that we need to calculate qt, but what the catch here is that actually it is not. You just need to check whether AT is satisfying the bound or not, and then the rest of the things means are assured by their construction and dependency. Like if we have this AT satisfies this, then we can construct qt, and then putting that qt back to equation 9 and 10, we can see that qt is satisfying this. And once we get a proof for this generalized statement, then there is no need to check other things, only need to check is A or the matrix AT. That's it. So suppose the first we need to show that for the integral mentioned in equation 1 converges for each t, so that qt is well defined. Now since our state equation like we are assuming that the state equation is now what we can do, go for directly, like if we assume that this is going to satisfy the state equation, then we can write the state equation means need to satisfy that condition of uniformly exponentially stable system. What we can do is that we can start from that argument and trace back and check whether Qt is complying with those requirements or not. So here this one must satisfy this condition, that is clear from our last few videos. Now for therefore for all t comma t naught such that t greater than is equal to t naught, we can have this t to infinity, integration running from t to infinity, this, right? And that is less than is equal to applying the property of norm, that is norm a to b is less than is equal to norm a into norm b. And remember, norm always return a positive number, positive real number, so there is no scope of having confusion that whether if you take it out of the norm, like whether this will be like how they will conform the multiplication. No need to think about this. And what you get, you just put these two values here, you will see that you will get this equation, right? Now that is equal to quite well can be written like gamma square by 2 lambda. So this one is equal to gamma square by 2 lambda. Now this calculation we can use to define rho in equation in previous video equation number 9. Since our Qt is clearly symmetric. Why Qt is symmetric? Because when you do this kind of things, like say if you take two matrices, they are not symmetric, like then you take this one, the transpose of that, or say this is the transpose, the original is this. Now if you multiply, what you will get is that a square plus b square, here you will have AC plus BD, here you will have AC plus BD, here you will have C square plus D square. So eventually whenever you do this, that is A transpose A into A, you are going to get symmetric matrix. It is actually a very straightforward one. So therefore Qt is symmetric. Now if Qt is symmetric and continuously differentiable for each t, then what we can get for today's equation 1, from this equation we can differentiate it. So if you differentiate it, what you will get? You will get q dot t will be will give you, actually what we need rho, we get, this is the value of rho. Now we need another few terms, like this gives us rho, the upper bound. Now we need the lower bound and also the rate of decay, because once we claim it is an exponential system from previous video equation 9, we need that your eta and rho to ensure the upper and lower bound of your Qt, and then you need the, when we consider equation 10, another constant V is required to govern the rate of convergence, right? So it is clear that if you do that q dot t, what you will get that it will give you something like this one, correct? That this q dot t, actually why we are doing so, because we are interested to find out the rate at which q dot t will converge. So while we are trying to do so, we did this, and what we got is this one. So now okay, so we have this here. Then this is the final outcome. Let it be equation number 2. I do not know why my pen is not working sometimes. So from that, what we can write is that ATQT plus QTAT plus Q dot T, basically that is what you are going to get when you do that. Means this is what we are supposed to get from if we do this. Sorry, xt. We should get this with here xt x, right? So if we see that one, then what we will get here is this is equal to minus I. So now what we can write further, that valid choice of V could be 1. Now we must show that there exists an eta, so it satisfies the lower bound. When the qt defined in such a way, it satisfies the lower bound. Upper bound for rho we have already proved and got some gamma by 2 lambda, but now we need to check it for lower bound. So for all t, we set up it in, and just a minute, again someone. So we are looking for this eta in a kind of we will show some of our mathematical, like we need to apply some of our mathematical skills to figure out that one. What we can get from this one, again, this is quite step-by-step evaluation. So this whole thing will become minus A transpose plus A xt qt. Now clearly this, once again, this could give you what? This could give you say this could be written like is less than is equal to this one. Is equal to this one, right? And this gives us what? This gives us this is further like this. So starting from there, we can reach to a conclusion that it is greater than is equal to these values. Now what we get, that phi a comma t approaches 0 exponentially as sigma tends to infinity, because we know that this guy, this phi a comma t, that solution, this is our premise. Like if you recall, we started our discussion with an assumption that our system is linearly asymptotic. Our system solution Qt is satisfying the requirement of being considered as a solution from a uniformly exponentially stable system. Then based on that we get it approaches. So obviously the solution is bound to converge to 0 in an exponential manner. Now if we do it, we will get this one, right? Let this be our equation 3. Means from the previous equation, if you integrate both sides, you will get this one, this guy, and the last one. So you will get this, because clearly this is what our Qt was defined in this way. Correct. Now see that okay, one thing you may get surprised, that why not we are like you are doing it xt, but try to understand that whole integration was carrying means we are carrying out the whole integration in terms of sigma, not in terms of t, right? So x as a function of t will appear to sigma as a constant function. Means for variation of sigma, x will remain unaffected. So if we evaluate the integration, what we will get finally, that is minus x transpose x is equal to, so that gives us Qt is always greater than is equal to 1 by 2 alpha I. So this gives us eta. What was our rho? Rho was, and now, and what is alpha? Alpha is that one which is giving us the upper bound of your AT. So we got all the three constants that is required to satisfy the condition of exponential stability. Now we will go and investigate the condition of instability. Quadratic Lyapunov function we can also use to develop the theory of instability. So again, let us take, and also I would like to mention that there is no such hard and fast rule that Qt must be real. It can be complex also, but for sake of or ease of representation, I just write it in this way. So Qt it is symmetric and continuously differentiable, and such that if we have Qt less than is equal to p, let it be equation number our equation number 4. Yes, 4. Last equation, perhaps it was equation 3. Yeah, it is equation 4. So now it is like And also consider this one is equation number 5, where rho and v are finite positive constants. Also that there exists a TA such that QTA is not positive semi-definite. This line is very, very important for our analysis. Here I would like to clarify one thing, although the statement needs further clarification. Don't think that Qt is not positive definite doesn't mean that Qt is positive definite. Qt could be positive definite. It means Qt is neither positive definite nor positive semi-definite, right? Then one is not uniformly stable. And once it is not uniformly stable, then uniformly stable is like the outermost set that you can have, or means in case of nonlinear system we can show, or means even in case of, sorry, not nonlinear, in case of dynamic system the outermost class can be stable system. Then there will be a subclass of uniform stable. Then there will be much more stronger or rather better class of your what system, that uniformly exponentially stable system. Actually I'm suffering with kind of fever and feeling means suffering with cough and cold, and also my voice sometimes gets choked due to excessive cough. Means sometimes I may fumble. Oh, please try to understand, and if you do not understand, then get back to me during discussion session. So now we need to prove it. So two way we can have here that either what are the two ways. In case of linear system it is quite easy that we got A and we impose some, what we discussed in our last theorem, that imposing a certain bound on A that serves our purpose. Or else what we can do is that we can go for means we get this kind of structure, and means you can consider it's like a reverse application of Laplace theorem. Suppose we are having such that our equations are almost structure wise, these equation 4 and 5 are quite analogous to equation 9 and 10. Only thing that the lower bound we cannot write, because here you can see that, as I have mentioned, Qt is not neither positive definite nor positive semi-definite, so that makes Qt free from that kind of bound. Like Qt can be sign indefinite, and therefore it would become very difficult for us to figure out such kind of any single bound for Qt. So means particularly the lower bound. So that is why we deliberately avoid mentioning lower bound, because if we start talking about eta, then means we will not leave with other choice to consider any matrix that is not sign definite, or means is having sign indefiniteness. So here what we can prove that let xt be a solution of 1 with t not is equal to ta, such that this is the case when your QTA is not positive definite or positive semi-definite. this is the case where your Qt is not positive definite or positive semi-definite. Then what we will have here is that like from equation number 4 here, sorry, equation number 5, what we can write is that xt qt xt minus x naught, that the means energy minus initial energy, the total energy minus initial energy is equal to minus t naught this. Actually this x transpose qt xt, it gives you the instantaneous energy, although the term instantaneous energy is kind of oxymoron, because like how it can be can we be said it like, because energy, whenever it's energy, it comes with a sense that someone is storing energy or someone is losing energy, and it must be over a period. It is but even if you are talking about losing energy or gaining energy in terms of positive power or negative power, in terms of like means whether your system is dissipative or receptive, but still what is there, that is very important to note, that your system here is like your this one is actually quite interesting, that this instantaneous energy minus initial energy can be written in this way, and what you will get that this difference is giving you something. This is very interesting, that x transpose x, so this is like minus rho xt square is equal to this is less than 0. That means what, if you try to interpret your system physically, this implies that over the time your system, although it is means less than is equal to 0, but what you can understand that if we do the further consequence of this one, then you will be able to get it more clearly. Then you will see that this is giving us these values. Just if we try to do it step by step, just a consequence of that previous one. Let the previous one be equation 6. So we are having these values, right? Now this is true for all t is equal to xt0. Thus from here eventually we get this one. Let this be equation 7. So from 4 and 7, what we get is that x transpose x d sigma is less than or equal to 2 rho by v x d square for all t greater than or equal to t0. Now what we can show you that the state equation is not uniformly stable. We can prove it by showing you that xt itself will become unbounded. So this we what we are actually doing is by showing you that it is a contradiction of our argument. So suppose there exists a positive constant, finite constant gamma, such that xt less than is equal to gamma for all t greater than is equal to t naught, then let this be our equation 8. From equation 8, what you can write? From equation 8, you can write that this is less than is equal to 2p, 2 rho gamma square by v for all t greater than t0. And the integrand, which is continuously differentiable scalar function, must go to 0 as t tends to infinity. Therefore, xt must also go to 0, and that implies that our equation number 6 is getting violated, because if you see the equation 6, it gives you an impression that it is for large t, equation 6 is giving you an unbounded solution. So this proves the contradiction. Let me repeat once again. I think you are having some problem because my or health condition, I cannot means put much energy here that I should put. Now again qt for all t, qt less than is equal to rho, these all these are correct. Now here that let xt be a solution, means we are assuming that this is less than 0. So if this is less than 0, uniformly stable means what? Uniformly stable means it will be bounded, and that bound will be independent of your initial time. That is what uniform stability implies. So if that gives us the notion of uniform stability for a linear system, then what we can see that this is equation 5. From equation 5 we get this expression where v is a positive number, and consequence of this equation 4, what we will get? We will get minus rho xt squared is this. That is equation number 6. Now from equation 6, further consequence of equation 6 is what? We are doing this, we are taking this one, and we are trying to write it like in this form. Okay, now applying the concept of norm here. Well, one thing I would like to mention that generally what we know that a minus b, norm of a minus b is less than is equal to, here obviously norm of a plus b, right? So this gives us the whole thing, that is less than is equal to 2xt qt xt. From where we are getting this? If you get back to here, you will see that xt qt xt is less than is equal to xt. So we are getting this one is less than is equal to this value. Now that further implies that for all t greater than 0 we are having this. Now what we need to show as we are trying to do this proof by contradiction, we can show the state equation we can show that it is not uniformly stable if we prove that xt is unbounded. In order to prove that unboundedness by a proof of contradiction, what we do, we take a finite gamma such that our xt is less than is equal to gamma for all t less than is equal to t naught. So that yields an obvious result, this one, and therefore the integrand that is going to be which is continuously differentiable function must go to 0 as t tends to infinity. Therefore xt must also go to 0 as this xt tends to 0. It is getting violated by your equation 6 for large t, right? Therefore what we are having here is that it is not a case of a bounded solution. Now we'll consider one example to make it more clear. We take this one and then we take this qt is equal to this one. Then we need to consider that q2at plus atqt plus q dot t, that gives us this value. Now suppose our a1t, this element, is differentiable, and let us assume that there exists a finite constant rho, positive constant rho, such that a1t is less than is equal to rho for all t. Further, we assume that there exists a time point ta which our a1ta is less than 0. Now what would happen if our a1ta become less than 0? You can understand the whole sign definiteness of qt means like a1t is playing a pivotal role in determining the sign definiteness of qt. So if you make qt quite negative, like means a1t negative, then qt will lose its sign definiteness. So if we say a1ta for this particular time is less than 0, then qt is lost its sign definiteness. So that gives us what? That and a is a positive constant. There exists a positive constant b for such that we are having a1 dot t is equal to minus v. Let us also consider a2t greater than is equal to v by 2. Now we will see that this is easy for us to check the assumptions, and with this means values, or better to say with the condition imposed on a1t and a2t, we can verify the state equations is not uniformly stable. So now after that we will go to our time invariant case. Try to get my point. What I am trying to say here is that it's very simple. like if you have this one, so one means confusion that may arise in your mind that apparently AT is upper bounded by means by uh, gamma, sorry, by an alpha. It is upper bounded by an alpha. Today's video's first theorem. So if it is upper bounded by AT, I'm talking about this 2 cross 2 matrix, upper bounded by alpha, then what went wrong, or where we overlooked some like subtle things that results as this contradiction, that we need to find out. For only one time point, we are having A1t is equal to that Ta is less than 0. For all other time point, A1t is greater than 0. So we need to figure out that what went wrong. Now we would like to discuss our case for LTI system. So what happens in case of LTI system? It becomes pretty simple, because first of all your Q dot T will become 0 because it is a constant case, and you don't have any like that equation number 10 will become here equation, it will also become today's equation 10, right? Uh, that equation, like it was last day's equation 10. Now as your A is time invariant, there is Q will also become time invariant, therefore Q dot T will become 0, and this whole equation, instead of considering minus VI, what we can do, we can consider M is equal to M, where M is a negative means M is a positive definite matrix. Now the final theorem for linear time invariant system, given n cross n, M and Q are symmetric positive definite and satisfy all the eigenvalues of A have negative real parts. Conversely, if all eigenvalues of A have negative real parts, then for each symmetric n cross n matrix M, there exists a unique solution of sorry, this is, I took it from a book where it is established 10 as Q is equal to this one, like what we stated at the beginning. That is the same thing we are going to state it here. Furthermore, if M is positive definite, then Q is positive definite. Conversely, if all eigenvalues of A have negative real part, how we can interpret this statement? This statement can be interpreted from our last semester control class that the system has all its pole located left half of the S plane. Then for each symmetric n cross n matrix M, there exists a unique solution that is Q is equal to e to the power at m e at. Furthermore, if m is positive definite, Q is positive definite. So we need to study that one, study the proof of this one. It's very simple. Now, if we consider Q is what we need to show you is that first, if all eigenvalues of A having negative real part, then what you will have due to this, see what we know that all eigenvalues having negative real part, and even if A is not in diagonal form, I have discussed that how we can transform this one to diagonal form, and basically it will become something like e to the power a dt will be where your AD is equal to P inverse AP. A is not a diagonal matrix, but AD is diagonal, and therefore EADT will be a diagonal matrix with P inverse AP. So what we can write here, that even if it is not diagonal, then we can get a diagonal matrix just by suitably. EAT can be written as P EADT P inverse, and from that we can show that EADT will be diagonal matrix with entries is equal to the eigenvalues, like EADT will be look like this. For a 2 cross 2 case I am writing E minus lambda 1 t 0, E minus lambda 2 t. So with increasing t, this is going to 0. Therefore, if this is if we consider this statement to be true, that all eigenvalues of A have negative real parts, then this is bound to means become 0 with increasing time. Now means that integration, of course, not going to become 0, but the integrand is going to become 0, and the overall integration result will be finite, because the integrand is going to shrink, and therefore it will be like means finding out the area under the curve, that where the curve is exhibiting converging tendency towards 0 value, right? So here you can see that this gives us this result. Now we need to show that this is obvious. So now let us show that Q, this equation 11, is a solution of this one. So in order to show that, what we can do is like we do it like ATQ plus QA is equal to this one. Now here we are assuming that 20 means this 11 is a solution, then we can get this value 80q. If you consider 11 is true, then this q can be written like this way and again in this way. Then further you can sum it up like this form, right? And that gives you something that is less than is equal to minus m. Now therefore definitely we can say that 80q plus qa is negative definite. Now we need to prove that this solution is unique. Here I need to do a few steps. Actually I am feeling seriously ill, so I cannot do. Now let us consider whenever you need to prove that solution is unique, you should go with a contradiction that solution is not unique. So in case of non-unique solution, you need at least have more than one solution for a given equation. So let us consider that QA is also another solution other than Q that is given in equation 11. QA is another solution, and let us assume QA is different from Q. QA is not equal to Q. And then we will try to prove that QA minus Q is equal to will become 0. And then our work will be done. Now see what we can write here is that if QA is a solution, then you can write the same thing for QA, that is QA A plus A transpose QA is equal to M. So then you will get QA minus Q A transpose plus A transpose QA minus Q is equal to minus M. Minus of minus M is equal to 0. So, but from this what you will get? You will get E A transpose, sorry, T greater than is equal to 0. Now from which we can get is that E8 TT QA minus Q EA T 0 for all t greater than is equal to 0, and therefore if we integrate both sides from 0 to infinity, what we will get is that 0 is equal to, I know what you are going to say once I complete this form, so hence QA is equal to Q. So obvious question that will come in your mind, that it was clear from this line what was so special, like QA minus Q, Q A plus A transpose QA is equal to minus M, and QA plus A transpose QA is equal to minus M. So both are equal. Then why not we go for claiming that QA means why this step is not sufficient to claim Q is equal to QA. So I leave this as a task for you to figure out that whether this statement was sufficient to conclude that Q is equal to A. Even you can pick up a small example by yourself and try to show that this writing a single state is not means enough to prove that Q is equal to QA. Well, now I will go and means I'm preparing a worksheet. I'll circulate it to you as soon as possible.